Hey everyone, welcome to my talk on finding fast radio bursts faster. By the end of this video, I plan to cover what fast radio bursts, or FRBs, are, the major pain points in implementing search pipelines, and using Julia and CUDA.jl to accelerate this process. As a quick introduction, my name is Kiran, and I'm a EE PhD student at Caltech. My work is mainly focused on instrumentation and electronics, but as a longtime Julia programmer, I've been recently going down the rabbit hole to see what projects in radio astronomy could use the Julia treatment. So your first question might be, what on earth are fast radio bursts? The short answer is that FRBs are highly energetic, millisecond-long pulses in the radio sky that come from cosmological distances. By highly energetic, we mean that FRBs release as much energy in their few millisecond duration as our sun outputs in 3 days. This is intriguing for a couple of reasons. First, they are a billion times more energetic than the pulses from pulsars. This implies we can detect FRBs from the edge of the universe, which has all sorts of juicy scientific implications. The second big question is, why don't they all repeat? We've discovered only a handful that do, indicating some very different mechanism from pulsars. So your follow-up question then might be, why are all these discoveries happening now? And the simple answer is that we're just not used to looking at the transient radio sky. Astronomers have primarily operated under the assumption that the sky doesn't change, but once we started looking at pulsars, this began to change people's strategy. As we don't know what's creating FRBs, we must observe the entire sky in real time to find them. This is a colossal undertaking as we lose sensitivity by trying to watch more of the sky at once, and of course the immense computation problem that comes with it. To solve these issues, we are designing several new instruments. The CHIME telescope in Canada is probably the most famous, but new projects such as Caltech's DSA 2000 and the Galactic Radio Explorer, both of which I am working on, aim to hunt for FRBs on even more massive scales. While many big data problems are associated with finding FRBs, the first prominent one is de-dispersion. When these pulses are generated, they light up a chunk of frequencies all at once. Then as they travel to Earth, they pass through ionized interstellar media, spreading the spectral content out in time like a prism separates white light into a rainbow. So when we receive the pulse, we capture a section of a parabola, starting with the highest frequency that descends in time. This smearing of the pulse can cover several seconds. To characterize the FRB, we must remove this dispersion effect in a process called de-dispersion. We can parameterize the parabola using a constant called the dispersion measure, dm, which is related to the amount of ionized media the pulse traveled through. If the pulse originated from far away, it encountered more of this plasma, implying a higher dm. We can compute the dispersion delay between two frequencies using the relations shown here. To take a quick look at what a chunk of data looks like, we can plot some synthesized dynamic spectra. Here I'm making a short Gaussian pulse covering about 300 MHz of bandwidth centered at 1.4 GHz. This pulse has a dm of 500, manifesting as a delay of about 300 milliseconds. To start to understand this pulse, we need to de-disperse. Because we know the dm was 500, we can shift every subsequent frequency channel back in time by the appropriate dispersion delay. To have the same amount of data as we started with, we would need to grab points outside of the sampled window, so we'll use circ shift here to roll the data back onto itself. As long as the pulse isn't over the boundary, this is a quick and dirty way to not mess with the data shape. Now we can sum down the frequency axis to look at an analog of total power for this pulse. As the peak is high, we could reasonably say that an FRB was detected at this peak starting time. Of course, in reality, it's never this easy. So let's look at a chunk of spectra from a real FRB from April 2020. This was captured by the STARE 2 telescope from Caltech. Do you see a pulse in this data? I certainly don't. So how do you know the dm if we don't see a clear parabola? And this is precisely the crux of the problem. Just looking at what seems like a stream of noise, we need to integrate down all possible dm curves to see if anything adds up. Not only that, but we have to do this for every single starting time in real time. This has an algorithmic complexity of O of all those things, which means that this does not scale well. Despite the complexity setting us up for failure, we can truck forward with a naive CPU implementation. Here we'll make a quick function called circmod that we can use when computing the shifted indices to match the behavior of circshift. We could have also used offset arrays here, but we'll keep it simple. So for every dm and starting time, we perform our sum that follows the dm's curve and place that sum's result in our output. Here we're building an output matrix whose columns represent the collapsed frequency axis and rows represent dm. As the output may be all over the place, we can write a quick function to standardize our results in the time axis. So our power levels are in units of signal to noise. Then, given several dms to try, we can perform our search. This is what the transformed output looks like on the original fake pulse. This plot's maximum indicates the DM and starting time that produced a maximal SNR. As there could be multiple pulses in a given time window, we would need to run some clustering and peak search analysis to create a list of potential candidates. So benchmarking the CPU approach, it's expectedly awful. Over 14 seconds to process a second of data. But of course, we can improve this by doing all the typical CPU-based loop enhancements. This involves steps like pre-computing a plan, like FFTW, where we solve for all the shifts beforehand. Also, we can bring out the big guns with loop vectorization and make use of all of those thick vector instructions. Doing this can shorten the solution time to about 2 seconds, but that's still twice real time. To see more improvements without fundamentally changing our strategy, we need to look at GPUs. So in our approach here, we're performing the same action, summing down frequency for every DM and starting time, which hints that this might parallelize well. As there isn't an obvious way to solve this problem with the array abstractions, and because we want fine-tuned control of everything, we need to write our own kernel. So to start, we'll decide on the block size. Having one of the dimensions as DM makes sense, and the others can represent samples divided by however many threads we'll give per block. This is to say that every thread will be responsible for 1 pixel of the output. This is nice because we don't have to think about atomics or anything like that. We'll do the typical step of determining which point in the output we're referring to based on our index. Unfortunately, as we wanted our block size to be the correct number of multiple of threads, we'll have to create more threads than there are pixels, so we bail early if we're out of bounds. Then, we perform the same sum as before. However, we changed our strategy here in that sums that go out of the window will add a pre-computed mean instead of looping back around. This is to keep the SNR reasonable for all those curves and ensure that the memory access pattern remains coalesced, which we need for GPU programming to be performant. In the spawning code, we can use the new occupancy API to determine the optimum number of threads to perform the execution. We can do this first step also of pre-computing the mean that the kernel needs. So how does it perform? Well, we need to pre-allocate the output first, solve for our plan, move the spectra to GPU memory, and then call our kernel. As a nice added bonus, our previous code for standardizing the output just works with CUDA arrays via the array abstractions, and we can compose it with the kernel we've written here. So instead of 2 seconds, we're down to about a millisecond. Quite a considerable improvement, I'd say. We are much better than real time now, but how much faster can we make this? The hot part of the code is obviously the sum itself. Mainly, we're doing 2 global lookups to global memory via the plan and the source spectra. There's not much we can do about the source, but we can be a little more clever with the plan. As all threads in a given block share a DM, we can create a chunk of shared memory to hold that row of shifts. Then we can write a clever little for loop to parallelize those global memory lookups to populate the shared memory. Then in a sum, we're accessing the shared memory instead of global memory, which is significantly faster. How much faster? About 150%, which is still an incredible number, but let's keep squeezing. Following the popular recommendations, we can inbound all of our loops, ensure all the integers are 32-bit, sprinkle around magical LLVM intrinsics, and this gives us another 175% improvement. So, after all of this, let's look at the FRB from before. Can we find it in real time? So, we'll process the first half of the time window so we don't need to worry about summing out of bounds, and we'll limit our search to DMs of 200 to 400. We can see a nice peak here at a DM of about 340, starting at 70 milliseconds or so, which matches the published results from this pulse. And we performed this search in about 2.5 milliseconds, covering 400 milliseconds of data, which is 160 times faster than real time. So if we were to compare this library to the industry standard, a CUDA library called ddisp, we could utilize their test program that dedisperses 120,000 time steps over 1,024 frequency channels by 32 DM trials. It accomplishes this in about 60 milliseconds. Performing a dedispersion of the same size with our code does it in 10 milliseconds, which is a 6 times improvement. Not bad. So from here on, there are a few steps forward. Given the complexity, we're reaching the bottom of what's possible, so better algorithms are the next step. A few popular ones are the fast DM transform, for which I have a CPU-based Julia implementation for, and tree dedispersion, which backs the Chime search pipeline. Usually you start to find trade-offs between these faster algorithms and sensitivity. So after all of this, we're on track to writing an end-to-end FRB search pipeline in Julia. As mentioned before, we need to do some clustering and classification after dedispersion, and of course some radio frequency interference mitigation beforehand. All right, well, thank you for your attention. If you find this interesting and would like to help with this project, please check out my ddif.jl repo. PRs are, of course, more than welcome. And also a shout out to the whole Julia Astro community for helping me with this project. Thank you.